lift the top edge up. Okay, so I got a little bit of a target.
I can only go so high.
That's good. We're right there. Now, hold on to the edges. If this goes south, it's because you guys let go of the blanket. Okay? So, what's the initial momentum of the egg?
Zero.
Zero.
Wait,
What?
are you throwing this like hard?
Not initially, but I will. Okay?
Uh-oh.
So, I'm going to have the initial momentum of the egg is zero. Okay? Zero.
Okay.
I'm going to give it some impulse, right? I'm going to take it from zero up to some value. What's the function of the blanket?
Cradle.
Cradle. To change the momentum of the egg, right?
Alright, girl, I don't want to
Okay? All right, so you ready? First time I'm going to throw it fairly slowly.
If you hit a student, do we get to go home?
Yes. Okay? You ready? Okay. Now catch it. There you go. That would have been bad.
Okay. Now,
Okay.
No, we gotta catch it.
So, which one imparted the greater momentum? Me or the blanket? Or was it the same? Same, because I took the egg from zero to something. The blanket took it from something to zero. Now, I'm going to do it again. I'm going to throw it harder. Okay? You ready?
Remember, we gotta catch it.
Okay? All right?
Is it ever gonna break?
Hold on. So, what happened to the amount of force that I exerted on the egg?
Like that?
Yeah, just hold that edge up.
Oh, okay.
A greater force.
I exerted a greater force. Therefore, there was a greater change in momentum. Okay, so this, I'm going to bring the heat. Okay, you ready?
Can you hit me?
See,
No. So hold on to the blanket.
let me, okay.
You ready?
Yeah.
Okay. All right. So no matter how fast I throw this thing, it's not going to break. Why?
Because the blanket slows it down.
Over a long period of time.
Yeah.
Right? Okay? So if I decrease that momentum over a long period of time, that means that line is shallow and it takes less force. Now, however, if I take the same egg, we're done, we're good.
Oh.
And I just drop this egg.
Don't get on my way.
No, okay. If I drop this egg just from this height, what's going to happen?
No, it's gonna, yeah.
Oh.
Okay?
Come on, Elliot, back there.
Bye-bye egg.
It shatters.
We
So,
have another egg?
no. So here's the difference. If I throw that egg as fast as I can into the blanket, it doesn't break.
See?
But if I drop it from this height here, very shallow height, hits the table, it shatters. What's the difference?
Force normal's a lot harder.
Nothing but
No, not force normal. It has to do with time.
momentum is changing faster.
The momentum changes very rapidly when it hits the solid table. Momentum changes slowly when it hits the floor. Now, one time I was doing this, and I was having trouble with my shoulder, so I couldn't throw it. And this kid says, "Oh, I can do this, Burkamp." I said, "Okay, great." So I had a kid standing over there by the door. I said, "Whatever you do, don't miss the blanket." He goes, "Oh, Burkamp, I'm a great baseball player.
Right
I'm
over
a
the blanket.
shortstop." Oh yeah. So he throws it, sails it underneath the blanket. It hits right at that gap between the floor and the door. There was egg splattered all over. I mean, it was just like a crime scene. There was egg spread out for like 10 feet on the inside, like bam. Bad things happen. Okay, all right, we're good. Back we go.
Did he ever do another demo again?
Nope.
Who are you gonna have?
It wouldn't have been so bad if he hadn't bragged about, "Oh, I'm a great baseball player," and all this good stuff. Like, really? Are you?
If I threw it, that'd be expected.
Yeah.
Okay,
If I threw it, I would hit the blank.
now, this is a situation where you all intuitively understand that force times time equals change in momentum. You understand this. I just have to convince you that you know this. So, has anybody done gymnastics? Okay, done gymnastics. When you land, what do you want to do with your legs?
Straight
Bend
legged.
them, yeah.
Bend them.
You gonna snap your knees.
Okay, you bend your
Yeah,
knees.
you're gonna snap your knees.
Why?
Cause your knees.
In terms of this equation, why do you bend your knees?
Greater times.
Greater time, less force. No.
I'll hit you.
So if you look at what can happen if you were to look at a force time graph, right? And the area underneath the force time graph gives you change in momentum. So there's two ways you can view this. If you land with your knees bent, that means you're going to have a small force exerted over a long period of time, which is going to create a certain change in momentum. So you land, you bend your knees, you do this, right? Now, you land with your knees locked. What's going to happen in the amount of time it takes for you to stop?
It'll be a
Way
lot less.
slower.
It's going to be a lot less. So in that situation, that means you're going to have a much bigger force acting over a shorter period of time. But the change in momentum is going to be the same. Your body is going to come to a stop no matter what. The
So,
only difference is the time that's involved. Okay? So this is where you have to focus on what's staying the same. So if the change in momentum is the same, I can make this happen one of two ways. I can either have a small force act over a long period of time, like when I threw the egg into the blanket, okay? Or I could have a small amount of time, but that's going to require more force. So this is, every time you drive your car, you use this equation. You're going, Burkamp, I've never seen this equation before in my life. Sure you have. Okay, you just don't know it. So your car has a certain amount of momentum as a function of time, right? So you're going to start off and you want to end up with a certain amount of momentum. There's two ways you can do that. You can slowly increase your momentum as a function of time, or you can rapidly increase your momentum as a function of time, okay? So when you press the gas pedal, you're deciding, what do I want that rate function to be in terms of my change in momentum per unit of time? Do I want it to change slowly as a function of time, or do I want it to change rapidly as a function of time?
As rapidly.
Which one's going to require more force? The rapid change in momentum per unit of time, or the slower one?
Rapid.
Rapid. Ah, cool. Now, this is where the magic happens. We just said that force times time equals change in momentum, which is mass times V minus V naught. True?
see,
What we just established. Now, I'm going to divide both sides by time.
well,
M equals.
What's changed in velocity over time?
Acceleration.
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 So that's just F equals ma.
Oh my goodness.
Okay? That's it. It's just F equals ma. So the rate at which your velocity changes determines your acceleration. Your acceleration is determined by the amount of net force. Gavin.
So change in momentum over time equals ma. Oh.
So-
Basically everything equals F equals ma.
Well, kind of, not everything, but a lot of it does.
Oh,
Okay?
why?
Now, so we just established also that force times time on a graph equals change in momentum. So here's though where this gets glitchy, okay? This is assuming that you have a constant force. It's the same uniform force acting over the same amount of time. In reality, that isn't true, okay? And I'll give you an example. So when this golf ball hits the table, that force that the table exerts on the golf ball isn't the same the entire time, okay? Because it starts off slow when that ball first comes in contact with it, and then the force actually gets bigger, and then the force becomes smaller. So, but it's the same idea. So sometimes you see a force time graph written like this, where it's like a triangle, okay? But it's the same idea. if it's a triangle, you're still finding the area. The area is still the same. Now, this is where the math changes a little bit. So this change in momentum is force times time, okay? That's a rectangle, okay? You don't think about it, but oh yeah, that's just a rectangle. The dimensions of the rectangle are force by time. That's the dimensions of the rectangle. So this one, in terms of F, what we'll call F max, that's the maximum amount of force that's going to be exerted on the ball. How do you find the area of a triangle?
1/2 base times height.
2AB.
So this one, the area is still the same. So that would be 1/2 F max times time equals the change in momentum. So if you see, and some of your questions ask for this, if it asks for F max, all it's asking you to do, and don't flip out and go, oh my God, this is so weird. It's just the area of a triangle, okay? So 1/2 F max time equals change in momentum. All we're saying is that in reality, it starts with the small force, the force gets bigger up to a point, and then the force decreases. If it just says the same amount of force acts over the same amount of time, then it's just a rectangle, okay? That's it. All right. So let's look at a simple example. So we're going to have a car, mass of 10 kilograms. Let's say that it's moving at 6 meters per second. And the car is going to come to a stop. Okay? Final velocity is going to be 0. Cool. Got it. Nice.
One target's long.
Does the momentum of the car change?
Yes.
Yes.
Can you find the change in momentum of the car? Do you have enough information to find the
Yes.
change in
We have
momentum of the
enough.
car?
Yeah,
Oh,
mass
yes.
times
Got it.
Because change in momentum is going to be mass times,
V minus V naught.
which is going to be V minus.
So -6.
Now, here's what you're going to do wrong. You mark my words, this is what you're going to do wrong. You all giggle and go, Mr. Burkamp, we won't do that. Yes, you will. Because you're going to go, oh, 10 and 6, change in momentum is 60.
What the freak?
Yeah, that's what you're going to do.
60?
How?
Why would I do that?
Because this is not my first.
Yeah, I
6
see
to
how you
0
would
and
do
I would
that.
get 60?
So, what's the final velocity of the car?
0.
0,
Minus?
6. So it's negative 6.
It's negative.
Yeah, -6. Oh, I thought you
-6.
meant like, I'll get
Oh, I
60
thought you meant like any
velocity.
60 was wrong.
No.
Oh, okay.
You're just going to see 10 and 6 and say it's 60.
I thought you were gonna say out.
Now.
Whatever, never mind.
What's the initial momentum of the car?
0. Wait, 60.
The initial momentum of the car is 60 Newton seconds, right?
Yep.
So what would this look like on a momentum time graph?
It started at 60 and go down.
Start at 60 and it's going to come down here like this,
Yes.
Si, senor.
okay? Going to go to 0. At this point, could you find the slope of the line?
Yes.
Yep.
No? Oh, we don't know the time.
You don't know the time. Now, what's going to be the sign of the slope?
Negative.
Negative. What does the slope of a momentum time graph give you?
Force.
Force. So is the force going to be a negative value?
Yes.
Wait,
Which should make sense. Because which direction, the car is moving to your right, so if you're going to stop the car, which direction does the force have to act?
Opposite.
So your force has to be a negative value, okay?
we can find the time.
No, you can't.
What?
Having it wrong.
We have the velocity, like we have the initial and the final.
You're
What do you
right,
mean more-
but you don't have distance or anything else,
Wait, oh, I thought we had, never mind.
okay?
I-
Now, let's say that it takes 3 seconds for the car to stop.
Now we can.
Ah, now you can. Because force times time equals change in momentum. Do you know the change in momentum? Yeah,
Yeah.
that's negative 60 Newton seconds.
Divide
The
by
time is
3.
3 seconds.
Negative 20.
Seconds cancel out. I get,
-20 newtons.
which is the slope of this line. because it's a rate function, okay? So if I look at this and the seconds cancel out, that's gonna give me the slope of that line, negative 20 newtons, okay? So what we're saying is that if this is newtons per second, if you look at this in terms of newton seconds per second, we're saying that the force, that the momentum is changing negative 20 newton seconds per second. Dylan?
Does the cheese car have ABS? Well, I mean, wouldn't the line be more of a,
Just go with it. Now, listen to me very carefully what I'm about to ask you. If instead of 3 seconds, it took 6 seconds,
Okay.
what would that do to the change in the momentum?
Decrease, the slope would be less steep.
What would happen to the change in the momentum?
It's still decreasing the same.
Oh, the change in
The
momentum
change in
would be the
momentum
same.
would still be the
Yeah.
same.
It would just change slower.
It would change the full
Yes.
force.
So, because if you look at this, in terms of change in momentum equals mass times delta V. Is time a factor in that calculation?
No.
No. So, as long as the change in the velocity is the same, time doesn't matter. But, if it took 6 seconds, what would happen to the slope of this line? Instead of being here at 3 seconds, you're gonna end up way out here at,
Maybe less steep.
yeah,
because it would be less.
The slope would be negative 10 now.
Yeah. Okay? That's why you have to focus on what's staying the same and what's changing. Okay?
See, senor.
Makes sense.
that was confusing for a second. I thought you meant like that 10 seconds was gonna have
No,
to
no,
make
no,
a
no.
new equation and then we're gonna have to refigure it out.
No, 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 no.
Oh, we don't have homework, do we?
Oh, you guys.
He's literally grabbing
But it's Halloween, Bergkamp.
Huh?
It's Halloween.
Yeah, that's why it's not due until Monday. So you can go out and trick or treat and extort people for candy.
What's wrong with
Well,
this?
that's huge.
You never said anything.
Okay,
Oh, you haven't done so.
I changed this up and then I forgot to change one number. On question number 8, it refers to question number 6. That should actually be question number 7. So on question number 8, where it says the puck in number 6, that should be in number 7.
So
Okay.
on our paper, do you want us to switch it?
No, just where it says, any place on 8 and 9, where it says 6, mark out the 6, change that to a 7. Of course, I didn't realize until I printed this whole thing out. So on question 8 and 9, where it says number 6, mark out the 6, change that to question number 7.
Okay.
Now, on question number 1, where it says, can a mouse and have the same momentum as an elephant? Don't get nitpicky and go, well, if the mouse is really big. No, it's a normal sized mouse and a normal sized elephant, okay? Don't go, well, it's a tiny little elephant. No, okay? It's a normal sized mouse, normal sized elephant, okay? Don't
This is like Gary and Hank, right?
Kinda, yeah.
So the answer would be yes, right?
I don't know.
Yeah.
Anyway, all right, you're on your own, be free.
Mr. Burkamp, do you have any assignments
Why would
for
it be
me for
no?
next week
Momentum mass times
that I could take?
Exactly. So you just change the policy.
He said, don't be nitpicky.
That's what we did with Gary and Hank.
That's the assignment on Monday.
Thank you.
That's the lab we're doing on Tuesday.
Cool.
And then on Wednesday, I'm just working a problem in class and you won't have any homework on Wednesday.
Okay, thank you.
One problem in class.
But it's a big problem.
Yeah, this
I'll be
is
sick
the
then.
thing you keep asking for. What if that's the one problem? You're about to learn what that stuff.
Where's that at?
Huh?
I never once asked for the test to be one problem, because I get that one problem wrong.
I'm pretty sure you have it.